Hello. What follows is an introduction to trigonometric identities. To keep us organized, I made a list of the things that we're going to talk about in this video. So I will introduce some useful trigonometric identities. We're going to simplify some trig expressions. We will verify some trig identities, and we will also determine if an identity is true or false. Now, at this point, you're probably thinking, hang on, what are trig identities? That's a good question. They're basically equations that show two things are equal. One of the things is usually complicated, and the other is simpler. Just remember, trig identities are equations. So I want to start by introducing you to the most famous of the identities, and that is a Pythagorean identity. And as you're probably guessing, the Pythagorean identities are based on the Pythagorean theorem. So remember that unit circle we've been studying, right? There's a circle here. It has a radius of 1. Pretend that looks like a real circle. When we've drawn points on this circle, those are all ordered pairs. And remember that the ordered pairs are the cosine of theta and the sine of theta, right? The y value is the x value is the cosine value, and the y value is the sine value. But we can actually turn this into a right triangle, right? If I just draw this piece here, and I'm going to redraw it down here so you can see. I'll just pull that green triangle right off the circle and just draw it down here like it's geometry class. What we're saying is that the x value, this distance here on the bottom, is cosine of theta. I haven't established it yet, but let's put theta right on the, this is a theta. Let's put theta right on the circle here. Remember, that's our angle theta. That means this guy's theta right here. And the y value, that's the up and down value here, that's sine theta. And remember, this thing is a unit circle, so the hypotenuse is just 1. And now we can think of this in terms of a Pythagorean relationship. If I consider this cosine theta, this base here, just as labeled A, and this vertical leg, sine theta, labeled B, and the hypotenuse labeled C, we know that A squared plus B squared equals C squared. Our geometry teachers drilled that into our heads. Well, I'm just going to replace the A, B, and C with the green values that we have written on our triangle. So instead of A squared, that would be cosine theta squared, which we usually write as cosine squared theta. And instead of B squared, that would be sine of theta squared, which we write as sine squared theta. And then the C squared would just be 1 squared, which is 1. And this bad boy right here, this is our Pythagorean identity. This is the most famous identity that you'll probably work with the entire year. Cosine squared theta plus sine squared theta equals 1. It's a huge deal. You have to memorize this thing. That's the most famous Pythagorean identity. Now, notice we've used a plural right here, and we've said, we've said that there are Pythagorean identities. So there's actually more than one, but they're all based on this one. And I'll develop those in a second. But I can't say enough how important it is for you to memorize cosine squared theta plus sine squared theta equals 1. We're going to use this thing a lot. Let me show you how we can turn this Pythagorean identity into the other two Pythagorean identities. So essentially what we do is we take that Pythagorean identity, the famous one that I just mentioned, cosine squared theta plus sine squared theta equals 1. And if we just do a little algebra with this thing, we can transform this into the other two Pythagorean identities. So the first thing I'm going to do is I'm just going to divide all of these terms by cosine squared theta. And when I do that, this term, the first term, becomes 1. The second term is sine squared theta over cosine squared theta, but I think you'll remember that that's just tangent squared theta. And then this last term is 1 over cosine squared theta. And we've learned that the secant is the reciprocal of cosine. And so I'm going to write that as secant squared theta. And now we have a new version of that Pythagorean identity that we had. This is also a famous one. Not quite as famous as cosine squared theta plus sine squared theta equals 1, but still an important identity that we're going to use a lot. Now notice, like I said before, when we talk about what identities are, they are just equations, right? So I do have this equal sign right here. And usually one side's a little more complicated than the other. So 1 plus tangent squared is a little bit more complicated than secant squared theta. Same thing over here. Cosine squared theta plus sine squared theta, that's a complicated part of this equation. And the simpler side is just the 1. So these are identities because they're equations, but more importantly, they help us simplify trig expressions. Okay, so this guy here, don't forget, this is our second Pythagorean identity. And there's one more, and I'll do this basically the same trick on the next slide to give you the third Pythagorean identity. So again, if I start with that same famous Pythagorean identity and I do a little algebra, instead of dividing by cosine squared of theta, I'm going to divide everything by sine squared of theta. So I'll divide all these terms by sine squared theta, and then we'll see what happens when we do that. I think you probably can predict based on what we did last time how this is going to turn out. The cosine squared theta over the sine squared theta, that is actually a cotangent, right? Cosine theta over sine theta is cotangent theta, and we're squaring those, so this thing is going to be cotangent squared of theta. Whoops. Sine squared of theta divided by sine squared of theta, that just turns into a 1. And then 1 over sine squared theta, that's the same as cosecant squared theta, right? Because 1 over sine of theta is just cosecant theta from our definitions. So this is another identity that we'll see a lot. The cotangent squared of theta plus 1 equals cosecant squared theta. Sometimes math books will turn these around. They start with a 1 plus, so they'll commute those. But it's the same identity. And so from here you can see that we can build the other two Pythagorean identities from the original cosine squared theta plus sine squared theta equals 1. All right, those are the Pythagorean identities. There are some other basic identities that we're going to learn today so that you can complete your exercises. When we started our discussion of functions, before we even started talking about the trig functions, we learned about even and odd functions. So I just want to remind you how that works. A function is odd if, when you plug in a negative x into the function, right? You plug in the opposite of x into the function, that equals the opposite of f of x. And a function is even if, when you plug the negative x into the function, it equals the same as the f of x. So we learned that characteristic of even and odd functions back when we studied functions in general. And it doesn't take long to figure out that these trigonometric functions fall into those categories. So the even odd identities that I want to state for you, basically there's one for each of the trig functions. So we'll start with the sine function. The sine of negative theta happens to be odd, so this is going to be negative sine of theta. Right? And just know that sine is odd. Cosine turns out to be an even function, so the cosine of negative theta is the same as the cosine of theta. Cosine's even. And just in case you're not sure, just go to your unit circle and test it out, right? If you do the cosine of something like pi over 4, you should have that memorized, and that should equal the square root of 2 over 2. And if you do the cosine of negative pi over 4, because we're still on the right side of the coordinate plane of the y-axis, the cosine value is still positive, so that one's also the square root of 2 over 2. So this even and odd structure or characteristic that we have for these functions comes right off of what we've been working with before. Okay, so let me finish these off. The secant function, let's do tangent first. The tangent function, tangent happens to be odd. If you plug in negative theta into tangent, you're going to get the negative of whatever tangent theta is. And in particular, you can just test this out with pi over 4 also. The tangent of pi over 4 is the square root of 2 over 2 divided by the square root of 2 over 2, which is 1. But the tangent of negative pi over 4 is down in the fourth quadrant, and that's going to be negative square root of 2 over 2 divided by the square root of 2 over 2, which is the opposite of the original. It's negative 1 instead of 1. So those are sine, cosine, and tangent, and then the reciprocal functions have similar characteristics. So the secant function, which is the reciprocal of the cosine function, that's also even. So the secant of negative theta is the same as secant of theta. The cosecant function, which is the reciprocal of the sine function, is odd. So that's going to equal negative cosecant theta. So this one's odd, this one's even, this one's odd. And then cotangent is also odd. Cotangent of negative theta turns out to also be an odd function. And so as I try to memorize the characteristics of these identities, I usually just remember that cosine and secant are even and everything else is odd. Cosine and secant are even and everything else is odd. But these are the even odd identities that we'll use to simplify expressions. Now I've mentioned this reciprocal relationship that some of the trig functions have, so let's just formally list those right now, the reciprocal identities. These are things that we've already talked about before in our discussion of the unit circle, but just to remind you that the sine of theta is the same as the reciprocal of the cosecant of theta, and therefore the cosecant of theta is the reciprocal of the sine of theta, right? We've already studied this. I'm just formally stating it here, so we'll have an official list of identities. Cosine is the reciprocal of secant. And therefore secant theta is the reciprocal of cosine theta. And then we know tangent and cotangent are reciprocals. So these are already things you probably know. I'm just formally letting you know that these are also identities because they're equations that relate these things, and usually one side's simpler looking than the other. Most people would rather work with tangent of theta than 1 over cotangent of theta and vice versa. So these are the reciprocal identities. It's not a secret, nothing special here, just reminding you that we've already covered this stuff. And if maybe you have forgotten, and so it's good for you to see these. And then there's one other category of identity that I want to introduce today, and that's just to formalize the quotient identities. So the quotient identities have to do with tangent and cotangent, and this is an important fact for us to know, that the tangent of theta, remember, from our unit circle, that's the y over the x, so that is the sine of theta over the cosine of theta. Again, you probably already know that, but we're formalizing this and making sure that you know that this is an identity now. And then, similarly, the cotangent of theta, since it's the reciprocal of the tangent, it's going to be the reciprocal of the fraction, the quotient, which would be cosine of theta over sine of theta. So these two facts are called the quotient identities. And again, as you're looking at these identities, they're equations, and one side looks complicated and the other side looks simpler. So those are our identities. Now what? Well, let's run through some examples of what we're going to do with these identities, and then we'll wrap this video up. One of the first things we do with these identities is we simplify expressions. So what I mean by that is we take something that kind of looks complicated and messy and we turn it into something that looks a little simpler just by using these identities. Let me give you a quick example. Let's say you have this expression, sine of x times cosine of x times secant of x. And we are asked to simplify this thing. Now, this is not an equation. There's nothing to solve for. We just want to take what we see here and see if we can make it look a little simpler. And so what I'm going to do is I'm going to apply some of these identities. In particular, let's start by applying this reciprocal identity. So remember, the secant of x can also be written as 1 over the cosine of x using that reciprocal identity. So all I've done, I haven't changed the value of this expression at all. It's still sine of x times cosine of x times secant of x, except I've written secant of x in a different way. And then what I notice is that if you multiply cosine of x by 1 over cosine of x, those cancel, and that turns into a 1. And I end up with a simpler expression, which is just sine of x. So I took something that's a little bit more complicated, used an identity, oops, that was supposed to be a check mark, used an identity, did a little algebra, and I came up with something simpler. And that's what we mean by simplifying expressions. Let me show you one more. Here's another example of simplifying some expressions. So let's take the cosecant of x plus the cosine of x times the cotangent of negative x. And let's see if we can simplify that. So the first thing I notice is I have this cotangent of negative x, and I remember that I have an even-odd identity that'll turn that into something different. So this thing can be turned into negative cotangent of x. And when I multiply that by cosine of x, basically that makes that whole term negative. So this simplifies to cosecant of x plus, minus, right? Minus because we multiplied by the negative sign. Cosine of x times cotangent of x. Now, one of the things that's usually helpful here is when you've got the expression written in terms of other trig functions, it's nice to see this in terms of sine and cosine. So I'm going to use a reciprocal identity to turn cosecant of x and a quotient identity to turn cotangent of x into things that have sines and cosines, because I'm more comfortable with sine and cosine. So cosecant of x is the 1 over sine of x. I'm not doing anything to cosine of x right now, but what I'm going to do here is turn the cotangent of x into cosine of x over sine of x. And now I can multiply these two together and make this a cosine squared of x. So I have 1 over sine of x minus cosine squared of x over sine of x. And since these are fractions with the same denominator, I can subtract them. And I can just write this as one fraction, 1 minus cosine squared of x over sine of x. Okay, now we are not done, because this bad boy right here can be reduced. And I'll show you on the next slide how we're going to do that. So we left off with 1 minus cosine squared of x over sine of x. And now I want you to think back to earlier in the video when I told you to memorize that important Pythagorean identity, cosine squared x plus sine squared x equals 1. I know we used it with theta in the parentheses. The variable that's in there doesn't matter. We can use x, we can use theta. The relationship is what's important. Now watch this. if I just subtract cosine of x, cosine squared of x from both sides, I end up with something cool. I end up with sine squared of x equals 1 minus cosine squared of x. Now I wrote this over here on the side because I'm going to use this fact to replace this with sine squared x. So I just demonstrated how that Pythagorean identity will allow me to replace 1 minus cosine squared x with sine squared x. And sine squared x over just regular old sine of x reduces, right? There's two of these bad boys up here, and there's one of them here, so I'm going to divide one of them out, and I'll end up with a final simplified answer of sine of x. That whole thing that we started with, it took 2 slides to get there, but I've reduced it down to just sine of x. In case you're not sure how I went from here to here, just remember that sine squared x means sine of x times sine of x. There's 2 of those guys. And then we had sine of x on the bottom, so I just canceled these out. And that's how I ended up here with sine of x. So this particular example, I used a reciprocal identity, I used a quotient identity, and I used a Pythagorean identity to simplify this down to just sine of x. Lots going on in that problem. Okay, what else are we going to do? So one of the other things that we often do with identities is we're given some equation, we're asked to verify that it's true. So for example, oops, got to hit the right pen there. For example, I'm going to verify for you that cosine of x minus cosine cubed of x is the same as or equals cosine of x times sine squared of x. And the strategy for verifying identities boils down to this. You're going to work on the left side and do the simplifying process until it looks like the right side. So I'm only going to work on cosine of x minus cosine cubed of x. I'm only going to work on that part. And when I make it look like this side, I'll be done and I will have verified that this thing is true. And basically that means I'm going to do a bunch of algebra involving these trig functions until I can get it to look like cosine of x times sine squared of x. So one of the things I notice is I have a binomial here with that minus sign, and they have a common term of cosine of x. So what we're going to do is factor out one cosine of x term. And when I do that, what's left over is, right, if I divide this one by cosine of x, I have a 1 left over. And if I divide this one by cosine of x, I end up with cosine squared of x left over. So I used factoring to turn this left side, the original left side, cosine of x minus cosine cubed of x, into cosine of x minus, or times 1 minus cosine squared of x. In the last slide, in the last example, I showed you that 1 minus cosine squared of x can be turned into sine squared of x. And so with that one little trick, by factoring and using the Pythagorean identity, I've got it down to what we wanted, which is that cosine of x minus cosine cubed of x equals sine squared of x. What we usually do is we write the left one down and then we keep equating it until we get to the one we wanted. So I did verify that this is in fact an identity. I worked on the left side and turned it into the right side. Along those lines, another type of exercise that we're going to be working on is to determine whether an identity that you're given is actually true or false. So you're either going to be able to work the left side so that it ends up being the right side, or you'll end up in a contradiction or something that's impossible, and you won't be able to make it true. So let me give you a quick example. I'm mumbling here a little bit. But let's say we have cosine squared, that's not cosine squared, cosine squared of theta minus sine squared of theta over 1 minus tangent squared of theta. The question is, does that equal sine squared of theta? So we're trying to show, either trying to show or trying to disprove, that this left side equals the right side. And, accomplishing this isn't always easy. So you might try 2 or 3 or 4 things before you arrive at the actual best strategy for completing your task. One thing I'm going to do, which doesn't look like it's possible, is I'm going to factor the numerator. And I'm going to specifically factor out a cosine squared of theta. Now, when I do that, you can see that if I factor out a cosine squared theta from that term, I'm left over with a 1. But you're probably saying to yourself, dude, there is no cosine squared of theta to take out of this second term. And you're correct that there isn't. So what I'm going to have to do is I'm going to have to fake it. In other words, remember, factoring sort of means dividing. So I'm trying to pull a cosine squared theta out of something that isn't there. And so basically I have to put it in as a denominator here. And you can verify that what I did is accurate if you just distribute this back. So if I distribute this back, cosine squared theta times 1 is my cosine squared theta right here. And cosine squared theta times sine squared theta over cosine squared theta is also sine squared theta, because those would cancel. Now, it might not be obvious as to why I did this, but take a look at what I end up with here. Okay, so I did a little factoring, a little crazy factoring, but I did that because I want to use one of my quotient identities right here. And sine squared theta over cosine squared theta, that's just tangent squared theta. And so what I arrive at is cosine squared theta, the guy that I pulled out, times 1 minus tangent squared theta. And that's this one right here that I just turned into a tangent squared theta, over the original 1 minus tangent squared theta that we had on the bottom all along. Now remember, there's implied parentheses down here on the bottom. So this binomial can be canceled with this one. And so what I've arrived at is that this left side equals cosine squared of theta. Okay? Now that's good news or bad news depending on what you were hoping for. It's certainly not sine squared theta, and there's no way for me to turn cosine squared theta into sine squared theta. So I have to say that this is a big old false. The original identity that we were presented with is false, because I know that cosine squared theta doesn't equal sine squared theta. They're two different things. There is no identity that can connect those together. Okay, so we did a lot of stuff in this video. This stuff is not easy. It takes practice. This was an introduction. We're going to practice a lot of these techniques, verifying identities, determining whether something is true or false, and just simplifying trig expressions. We're going to practice a lot so that we get better at it, and then some of these more complicated problems will become a little bit easier. So hang in there. Just soak it in a little bit, take some notes, and practice some problems. And when we see each other, we'll talk. If you need anything, you know where to find me. Take care.